This lecture would be in English, so I will now switch to English, if you don't mind, for the introduction of Professor Pievani. Professor Pievani is currently professor at the University of Padua and is professor of philosophy of biological sciences. University of Padua is, of course, for those that are not Italians, here is one of the most prestigious universities in Italy. It celebrates this year its 800 years, so it's one of the oldest, even though the oldest is Bologna, I guess. And I'm graduated at the University of Federico II in Naples, which is also pretty old. Let's say they are all pretty, should be the next one. Let's say they are all pretty old. And Professor Pievani actually graduated in philosophy of science at the University of Milano, and was then from 2005 to 2012 associate professor of philosophy of science in the University of Milano Bicocca, before becoming full professor at the University of Padua. He has a large activity in the philosophy of science, specifically if I understood well from the CV, specifically in the field of evolution. So he's a Darwinian expert, let's put it this way, and how the Darwin theory has an impact in the philosophy of science. He has a huge activity in outreach. I think he spends a lot of time in science communication, and he has a very rich activity in he's in the scientific committee of several institutes. He's coordinator of Festival of Science in Genoa, which is one of the most important festival of sciences in Italy. And is author of an incredibly long number of books and publications, I think many of them for outreach, for explaining this philosophy of science to the general public. So I think it's a great honor to have Professor Pievani here with us in Darmstadt, and it will be a great pleasure to learn from you about philosophy of science. Thank you very much.
Thank you. Thank you so much, Marco, and thank you to you all for this invitation. Thanks, Michele, for the organization of this wonderful festival dedicated to Galileo, and thanks to Paolo for the visit that we had to the European Space Agency. It's a great pleasure and honor to be here because, as Marco said, we decided to organize, also in collaboration with the University of Padua, this festival. I'm so proud for that, because we are trying to explain our history in this year when we are celebrating the 800 years from the foundation of the university. And Italy is coming to be the second country after UK with 2 universities with more than 800 years. So, and we are trying to explain with my colleagues, with my rector, try to explain the meaning of our motto, that is Universal Universitas Patavina Libertas, that means academic freedom, research freedom in Padua is universal and is for everyone. So that's our keyword for this celebration. And tonight I decided to try to share with you exactly some ideas about my view about academic freedom and the foundation of academic freedom. Freedom of research, of teaching, freedom of discovery, and so on. You know, academic freedom is still under threat, is at risk in many countries. According to recent statistics, less than half of countries in the world are really democratic and really respect academic freedom and freedom of expression. And my approach to academic freedom will be serendipity, will be this quite strange concept that I think is very important in philosophy of science. And I thought that it would be interesting to start exactly with one of the most important moments in the history of my university. That is when the UNESCO decided to acknowledge to the University of Padua the World Heritage patent. So with this wonderful motivation, according to which the Botanical Garden of Padua is the original of all botanical gardens throughout the world and represents the birth of science of scientific exchanges and understanding of the relationship between nature and culture. That's interesting, that's important. So a place in which you can find together nature and culture, humanities and science, study of biodiversity, and so on. And it gave contribution to the development of many disciplines and so on and so on. In our botanical garden, we do basic science, of course, so we study new plants, biodiversity, but together, at the same time, applied science, for example, in pharmacology, and so on. So always interlinked. So my first point is that if you look at the history of our university, where, Galileo Galilei taught for 80 years, he spent what he said it was the most important and most interesting part of his career in Padua, with observation, the first observations, the first publications, and the first open teaching. And again, as Enrico Bellone wrote, an historian, an Italian brilliant historian of science that worked in Padua as well. Now, he unfortunately passed away some years ago. Basic science produces knowledge that can generate applications, and here at the European Space Agency, you are masters of that. But also new technologies can open up unprecedented observation spaces that generate unexpected knowledge. So academic freedom is related both to basic research, so curiosity, fundamental research, and to applied research. Just as an example, these are some of the lines of research that we are implementing in my department of biology. It's an excellent department in Italy. And you can find some lines that are applied science, biogas, or biofuels from algae and so on, and many others that are absolutely related to curiosity. We like to study taxonomy or sexual selection in animals or molecular clocks in Antarctic krill and so on. That's our way to do science. So why serendipity for me is one of the keys in order to understand what is serendipity. I'd like to explain this concept not just with theoretical ideas, but also with examples. One of the most interesting for me is the example of the researches by Osamu Shimomura, a wonderful biochemist, Japanese biochemist that won the Nobel Prize in 2008. And he has a wonderful story. In his Nobel lecture, he explained that serendipity was the secret of his career, because he survived to the nuclear bomb in Nagasaki just by accident, and he by accident decided to become a biochemist in a pharmacologist department, and then he went to Princeton in order to just to study for curiosity jellyfish, okay, so marine organism, and by chance he was able to understand that in a specific species of jellyfish, Aquaria victoria, there is a wonderful protein that is responsible for natural bioluminescence in these animals that could be activated by calcium and other elements, and then can create a flourish that could be managed in many ways. For example, now we can use this green fluorescent protein. We use it in any biological department for mapping gene expression, for studying signals between cells, and so on. So an incredibly useful discovery, an incredibly powerful application that started with a curiosity, that started just with an interesting question, a marginal question related to some animals. So that's the power of human curiosity and the possibility of application. So that's my first topic. So the priority of basic science could be based on this process of serendipity. The term has a curious history, because maybe serendipity is used as a term quite for everything. You can find restaurants, you can find shops, you can find films and whatever with this term. But the real history of the origin of the term is related to a novel, to a Persian novel that has been translated into Italian by Cristoforo Armeni in Venice, exactly in the same period that the Botanical Garden Foundation, and then to Galileo's times. And in this novel you can find the wonderful story of three princes from Serendip, that was the ancient terms for Sri Lanka today, that were able to discover by accident and sagacity many things that they were not looking for. And also they are able, if you look at the novel, these princes are able to look at the clues that you can find in nature, so be able to see teeny signs of something hidden, and they are able to predict the existence of entities that they never observed. That's exactly the original root of the term serendipity. So to be able to imagine and to predict the existence of entities that you never observed before. And I have Guido Tonelli here. So Higgs boson has been predicted many years before the observation. Gravitational waves have been observed many times, many years and decades before the observation. So today scientists are doing exactly the job of the three princes of certainty. They are able, by rigorous application of methods, by symmetries, by models, by comparison between hypotheses, they are able to imagine, to suppose, and to predict the existence of entities, of objects never observed before. So I think there is a strong connection between the original root of the term serendipity and what scientists do today. But what is interesting, more interesting, is that the original term has been coined by Horace Walpole, so an English writer, the founder of the Gothic novel. It's not so important tonight. But Walpole decided to use just this specific idea. Serendipity is a phenomenon in which someone is searching for something, someone has a research question, even an obsession to solve a problem, and during the pathway, during the research, he or she is able to find something completely unexpected, something that he or she was not looking for. That's the definition of serendipity. And for me, as a philosopher of science, what's satisfying so far is that if you look at the classical and fragmentary literature about serendipity, quite always serendipity is treated and has a collection of anecdotes, so just stories, very famous about penicillin. That is a very weak version of serendipity, because Fleming was exactly interested in this kind of research about antibiotics, antiseptics. So he found what he was looking for. So it's a quite weak idea of serendipity. Of course, he was able to find penicillin through an accidental and contingent way, through lucky observation, of course. But the question was exactly the same since the beginning. And in other cases, you can find even stronger process of serendipity. Another wonderful example of serendipity that we use in our department, in any biological department today, that was a revolution in biotechnologies, is gene editing. Gene editing is now a completely new landscape in biotechnologies. Is a technique of pasting copy of the DNA, and it was discovered 15 years ago in a very marginal line of research proposed by 3 or 4 microbiologists in Spain and United States, funded with, according to a calculation, with no more than 60,000 euros, so nothing, a real marginal lines of research, what we call basic research. In our department, we didn't have any position about microbiology before the pandemic, so something that we didn't consider. And then they discovered an immune system, a specific immune system in bacteria, because they discovered that bacteria 2 billion years ago evolved a wonderful system in order to respond to attacks by viruses. And they are able to pasting copy the genetic material of the virus and to have an immune memory of the attack of the virus. And then other scientists understood that this machinery with a nucleus, with a protein able to cut another guide with RNA that is able to implement DNA, could be applicable to complex cell, to eukaryotic cell, and then they discovered what we call today the gene editing. And today you can find 5 great companies in Wall Street stock exchange market that do just gene editing. So everything started with a poor funds for a marginal line of research, and now the landscape of biotechnologies has been completely revolutionized by this technique. So it's a wonderful story of how powerful could be curiosity, how powerful could be have a range, have a scope, larger scope of interest in science. Now just a few ideas about the theoretical part of this story, because it could be very interesting. Because in my field, in philosophy of science, we inherited a somehow unsatisfactory dichotomy that was proposed by a very famous mathematician and physicist, the Hans Reichenbach, one of the founders of probabilistic calculation. And he wrote that in science you can have two great domains: the domain of the justification, so the way to which you can understand how a product of science could be well-funded, rational, so you can rational reconstruct the scientific process afterwards. And according to Reichenbach, this is the only considerable part of philosophy of science. So just to study science postdoc. And then, according to Reichenbach, you have the context of discovery. So all the psychological machinery, all the methodology through which a scientist is creative. So he's able to understand something and to discover something. And according to Reichenbach, this content of discovery was quite irrational. So just matter for psychology or sociology, just for emotions, or it was the nocturnal part of science, according to his definition. Now we are trying to understand the nocturnal part of science. So we are trying to understand if it's true, and I think it's not true, that this is just an irrational part of science. Discovery is not irrational. Discovery can have patterns. We can understand some of the structures of discovery. I know it's very hard, because we know science, as Peter Medawar said, we know science just from the scientific papers, and scientific papers purificate science because they exclude all the interesting part of science, so the process of discovery. But I think it is very important to explain science not just from the results, but explain science and communicate science as a process, as a genesis, okay? And one of the reasons why we think that science is irrational is the fact that science is based on inferences, like induction, so a generalization of what is known, that if you look exactly inside the structure of the reasoning, has no logical necessity. You can be wrong always, okay, with induction. But we use induction. We are inductive animals. We use everyday induction, but it's not rational, because induction has no logical necessity, okay? It's a challenge, okay? It's a bet on nature. And the very famous story by Bertrand Russell, Inductivist Turkey, is very clear about that. So maybe you remember that Karl Popper building, because we now are on the building of Popper idea of science, was exactly built for solving the problem of inductivism. The problem of the fact that we do not have, even with deduction, so the inference through which you have a universal law, and then you apply universal law to specific cases. But also in this case you can be wrong in many cases. So according to Popper, the only logical structure that is true and that you can trust is exactly the logical reverse. So we can scientifically say just that the theory is false, not that the theory is true. So you can say that you have a general law, you have something, you have an hypothesis, and you have to try an observation that can refute the hypothesis. In this case, your conclusion is the only, according to Popper, the only logically exact conclusion that you can have. It's not a verification, it's a falsification. But on falsification, you can build a lot of science. And that's, according for me, still today, it's a very interesting idea, because if you want to explain science, even in pandemic times, in emergency times, when people are asking science certainties and predictions and reassurations, you have to answer that science has always to deal with uncertainty, with doubts, with provisional results that you have to implement, and you have to work by falsification rather than to try to verify always your ideas. But even in the case of Popper, what the missing piece was exactly the logic of discovery. Because even when you have to falsify something, you have to propose a new observation, you have to find something, and you have to falsify. You have to find an empirical anomaly. You have to understand errors, your anomalies, that are very important in science. So, the recent field that we are trying to study together with other guys in UK, ERC, funds and so on, is exactly this question. Can we formalize serendipity? One attempt that is very interesting has been proposed by this biochemist and sociologist of science, Henri Jacob, in the University of Sussex, that won a ERC grant for Serendipity, that was also reviewed by Nature, the journal Nature, in this way, Lucky Science. So scientists are trying to understand the role of serendipity in research. And that's interesting because Jacob, like me and others, we are trying to go beyond anecdotal evidence about serendipity. We are trying to understand if serendipity is true, is valid for basic, but also for applied science. And this is exactly the case, because you can find serendipitous discoveries whenever you have a good question, independently on the fact that you are on basic or applied science. And how is important curiosity-driven research? You know, there is also a very practical point behind this discussion. That is, how can I fund better science if I have 10 millions of euros? Is it better that I dedicate a percentage of this fund for implementing already in the mainstream of science or already established lines of research, or is it better that I find that I've decided to support also marginal lines just for good question of good curiosities or what else? So, and in this research, it's interesting because we are trying to propose a taxonomy of serendipity, because we have many different kinds of serendipity. You can have interdisciplinary serendipity. So, for example, a line of research in a discipline that by serendipity is able to find something very, very important in a completely different discipline. A very famous example is the connections in maths between physics and life sciences, for example, or discoveries just due to an unexpected path in research or in technological research, a completely open research, like in the definition of Barnabas Bush, or that is my preferred serendipity, the fourth one, when you find a solution to a problem that only later emerges. That's wonderful. So you find something, you do not understand what is the meaning of the finding, and then you discover that you found before a solution of a problem that later emerges, like in the case of shatterproof glass for a car or for airplanes. And another very part of this research is also what we call the ecology of serendipitous findings. So what are the underlying conditions that can promote serendipity? Of course, it's a paradox, because serendipity is unexpected, is unpredictable, so it's impossible that you can plan serendipity. Okay? So serendipity is unexpected. So, but we know today, and we are trying to understand that there are conditions in the ecology of the functioning of science that can make serendipity more likely. For example, to be able to train young scientists not just in big data and technical problems, but also in good questions. So what we call qualitative training for scientists. So not just data, but also good question in order to interpret data, because data, as Pasteur said, are not enough, okay? Because data don't speak by themselves. Data speak because you have something to ask to the data. So qualitative science. New systems of observation, of course. So what you do here. So new technologies are able to open new spaces of observation that are plenty of potential serendipities. errors, and what Salvador Luria, our wonderful Nobel Prize study in the United States with Max Perutz, define controlled sloppiness. So to be so rigorous, like some musicians that know very well their music, and so they are so skilled in music that are able to improvise. So they are able to be sometimes loose and to find something new. So a controlled sloppiness, it's a wonderful way to serendipity. Slow science, of course, because serendipity needs slow science. And also what is very interesting, serendipity is directly depending on interdisciplinary networks of scientists, because if you have different scientists with different points of view working on the same problems, it's more likely that someone else is able to show you a serendipitous aspect of the problem. So multidisciplinarity is another way to promote serendipity. And again, so we are trying to propose a theory of serendipity. We know that it's very challenging, but not for the first time we are trying to promote serendipity. Finally, my original point about the theory of serendipity that I'm trying to implement in this theory is ignorance. Because I think that the frequency of serendipitous discovery in disciplines is related to our degree of ignorance. In which sense? This is the principle that I share with my friend Henry Guy, that is the senior editor of Nature for Life Sciences, and we are working together on this principle that we decided to call the Ramsell principle, because in a very strange way, Donald Ramsell, we don't know why, but in a specific moment of his not so brilliant career in the United States as a Secretary of State during the war in Iraq, maybe you remember and you remember that there was the matter of the mass destruction guns arms for Saddam Hussein. And after this story, the Parliament in the United States called Ramsell for a dialogue, and the Senate, I don't remember, maybe a senator asked to Donald Ramsell. But then, at the end, did you know that the guns, the mass destruction guns, were there or not? And we don't know why, but Ramsell replied in a genial way. We didn't understand what he meant, but he answered, I don't know, because in life there are no knowns, so things that we know. Okay, so we have knowledge about that, we know something. But then we also know that there are known unknowns. So we know that there are things that we don't know. And this is true. This is true in science, because in many cases in science, and that's very interesting, in science, you have the means in order to understand that you don't know something. Okay? So you know that you don't know. Okay? So you have the way to understand that you don't know. But in other cases, in other rare cases, Ramsell said, there are also unknown unknowns. So things that we don't know that we don't know. And he said that about the guns of Saddam Hussein, he didn't know that he didn't know. So we don't know today what it meant. Anyway, but that's interesting because it's true, and it's a wonderful principle in science, because in science, in some cases you know that you don't know, but in other cases, in an unpredictable way, you understand that before you didn't know that you didn't know. And according to Henry Guy, that is the chief of the life sciences Nature, in order to have the cover of Nature, in order to publish Nature, you have to demonstrate that your discovery is of the third kind. So please be aware, because if you want to publish in life sciences Nature, you have to find something that is in the third category. But it's exactly, the third category is exactly what Popper wrote in a wonderful passage in Conjectures and Refutation, when he wrote that true ignorance is not the absence of knowledge, is the refusal to acquire knowledge. So science is based on ignorance, but it's a rational ignorance. It's a rational way to manage ignorance and uncertainties. And then the history of science, like the history of all human ideas, is a history of responsible dreams, obstinacy of error. But science is one of the very few human activities, perhaps the only one, we don't know, in which errors are systematically criticized and fairly often in time corrected. This is why we can say that in science we often learn from our mistakes, and why we can speak clearly and sensibly about making progress there. So progress in science is made of errors and correction of errors. So just some examples. In many cases we know that we don't know. Okay, like in life sciences, for example, in my field, now we are going to found a new great national center in Italy dedicated to biodiversity. So with PNRR money, with European funds, and it will be a great center about Italian biodiversity. In this case, we know that we don't know, because we know that we don't know a large part of the biodiversity, even in Italy, okay, and even more in a general sense, or in worldwide. According to many experts in biodiversity, we think that we studied so far 2.2 million of species, but out there are at least 8 or 85 million of species. So in this case, we are ignorant, and we know that we are ignorant, and we have the means in order to know that we are ignorant, and we have the ways to study more. So we know that we don't know, okay? In other cases, and now here with Tonelli and Paolo, we can share that in many cases we have discovered that we don't know, that we didn't know, that we didn't know. So in some cases, a rigorous application of models is able to explain to a community that maybe we can study, that maybe out there they are much more than expected. In this case, in terms of dark energy and dark matter. So new questions, okay. So, another example that is related to serendipity. So, my hypothesis is this one. The most important serendipities happen when you, in an unpredictable way, you discover that you didn't know that you don't know. Just another very famous example of a serendipity. In this case, it's a case in which you find a solution of a problem that later emerged. It's the case of the research of Edward Benedictus about ecology films. A flask was broken, and he observed that the pieces of glass were able to stay together. And he didn't exactly understand the meaning of the discovery, but he made the observation, and he decided not to throw away this observation, and he understood that the observation was the fact that a colloid film inside, within the glass, it was able to put the piece together. And then, many years later, he understood that this was a solution for the problem of the glasses in the first cars moving on Paris. And he wrote in the newspaper that there was a problem, but when an accident happened, then you have a disaster for the passengers. And he delivered the patent for the glasses, or unbreakable glasses, and he became a millionaire. And he became one of the most important experts in Art Deco in Paris. He abandoned science, and he dedicated to change his mind. Another wonderful example, quite mysterious. I discussed with Guido about that. So the cases in which mathematicians are able to anticipate physics. They work on languages, they work on possible words like non-Euclidean geometries, and then you discover that some of these languages are exactly the language, the mathematical or geometrical language that you need in order to describe physical realities. That's interesting. In this case, you have before the mathematical language, and then much later, even like in this case. This is another story of Padua research, because it was Tullio Levi Civita that suggested to Einstein to apply tensor calculus and some mathematics tools for general relativity. So that's very interesting, because in this case you have before the mathematical language and then the physical description. This is another wonderful quotation in which this wonderful French mathematician Jacques Adamant explained this quite miraculous, as Eugene Wigner said, quite miraculous efficiency of mathematics in order to anticipate reality. And he wrote, many believe the stereotype according to which the profession of the scientist would be like that of a painter who wakes up in the morning, opens the window, sees a wonderful landscape, and represents it on the canvas as faithfully as possible. So the stereotype of science has description of the reality. So data, observation. This is wrong, according to Adamar. The profession of the scientist, who certainly has seen many landscapes in his life before, so trained, is rather that of initially remaining close in his room to paint the best landscape that comes to mind at a given moment. And only after drawing it, he opens the window and he tries to understand if there are connections between the painting he made and the landscape that was already out there. So anticipation, simulation, proactive methodology in science. If he finds them, then he has discovered something interesting about nature, but also about the landscape, but also about the mind who painted it. That's interesting, that's wonderful. So according to Adamar, science is a continuous dialectic between mind and nature, As also Galileo wrote in a letter. So that science is a continuous fight between mind, so the question of a scientist, and nature, and the answers from nature. And so, just two final points, and then I stop. Someone could think that this is a romantic way about science, but this is not true. This is very practical, and it was already successful. So we have successful story that already taught this story. This is a very famous quotation by Vannevar Bush, so the engineer with Truman and other United States president that he was the main strategist of the great growth of United States as one of the most important power in science and technology for decades. And his idea was exactly serendipity. Discoveries pertinent in this case to medical progress have often come from remote and unexpected sources. And it's certain that this will be true in the future. So progress will be made as a result of fundamental discoveries in unrelated subjects, perhaps entirely unexpected by the investigator. So a very radical idea. A radical idea that if you want to transform your country in a powerful country in science and technology, you have to support basic science. You have to support curiosity. Okay, you have to support a large range of lines, because the most important application come from remote and unexpected sources. Okay, that's exactly the point. So chemotherapy, maybe you know the very famous story, chemotherapy was exactly the application of what Vannevar Bush exactly wrote 2 years before, 2 years later, because exactly a case in which the discovery, the accidental and dramatic discovery of the effects of some absolutely prohibited gases during the end of the Second World War led to the discovery that an application of this gas was, in the case of nitrogenous mustard-like, could be applicable to animal models of lymphoma, and then 2 years later we had the first embryonal application of chemotherapy in oncology. So another example of very unexpected source of a line of research. And finally, my preferred example is a recent example by Francis Arnold, a wonderful Californian biochemist that I had the privilege to dialogue with and in Venice, and we shared a lot of ideas about that. And she won the Nobel Prize in 2018 for chemistry. And the initial idea that Francis Arnold had was in the 70s when she came to Madrid and she fell in love with the Babels of Labrador Babels by Borges, with this idea that you can have a combination, you can have a library, and in this library you can have a combination of everything, meaningless with meaningful, and all in the middle. So you can have whole books, real books, you can have the Bible, you can have Dante, and so on. But you can have also books with just a sentence with meaning, or just books without any sense, okay? Like in Borges' idea of a library. And this idea that was a metaphor, okay, was an analogy. Then she found the same idea in John Maynard Smith and the possible combination of proteins. She found the same idea in Daniel Dennett, a colleague of mine, a philosopher, that in a book in the 90s wrote that it would be wonderful to build a library of genomes, like exactly the Babels of Borges, a library of genomes, with all the possible genomes, with a morphospace of every possible animals, and then to compare the potential library of Borges, the library of animals, with the real animals, and try to understand if the difference between the two could be interesting for science. And then we discovered that it's very interesting, because we discovered that, for example, in evolution, that natural evolution didn't explore some parts of the morphospace. And now we are trying to understand why. That's interesting. What Frances Arnold did, it's exactly the application many years later of Borges' library of Babel for enzyme evolution. And she had the idea exactly to build a library of enzymes and then to breed molecules exactly like breeders breed animals. So she breeds molecules rather than organisms. So with mutation, induction of mutation in enzyme, then the exploration of all the possibilities with this mutation, then new mutations, selection, new mutations, selection. So it's a kind of artificial selection, but in the lab and applied to enzymes. And she told me that for 2 decades in the beginning, other than future Nobel Prizes told that it was absolutely impossible, because according to the mainstream, if you have to build an enzyme, you have to a top down. So you have to plan and you have to build enzyme starting with a framework. Rather than here, according to Frances' idea, you have to build enzyme bottom up. So you have to breed molecules, and then you can find a library of molecules, and then you can find molecules that are even better than natural molecules. It was a completely crazy idea, and then you have a Nobel Prize in Chemistry in 2018. Why? Because she was able to find cheaper and cleaner products using induced evolved enzymes, new drugs, 11 spin-offs in her university just for drugs for many industrial products. So real green technologies, due to a serendipity, due to a metaphor, due to an interesting analogy between literature, Borges, and science. And now she's able also to anticipate evolutionary processes. That's amazing for me as an evolutionist. So starting with real enzymes, she's able to predict possible evolution of the enzymes. For example, now we use this technology for predicting possible evolution of viruses. Okay, because we know the genome, so we know the book, and then we can have all the possible books starting from the book of the virus, so the genome of the virus. So now we are trying to predict and to the pathways of viruses for future pandemics. Everything starting from a metaphor from literature. So now we have a protein library, and we have a morphospace for viruses, for genomes, and so on. So I think that's a wonderful expression of serendipity, very powerful. So my final quotation is from George Wald. It's one of my preferred quotation in a conference in Boston. This Nobel Prize for medicine for his discoveries about photoreceptors in human eyes say one of the most important sources of happiness is finding an unattainable goal. It's a statement that may sound strange. In this life there are many things that we desire: someone to love, a home, children. Many of these things we will be able to achieve, but somehow achieving them will never match the dreams that preceded them. Therefore, it's important to find a goal that never ceases to be such, which allows us to achieve some small victory, even if it will be only the episode in the general framework in an endless research. Science fulfills this role. The happiness of science, I think, is rooted also in serendipity. And I thank you much. And I'm open to any questions.